Everyone, I'm just going to wait a second because I had to end the meeting and restart it. So I know some people got kicked out. All right, I think that's mostly everybody. Okay, well, welcome back. Hope you had a good weekend. I had the joy of having to reinstall my operating system on my computer this weekend, which was an entire day filled with blue screens and reinstallation of software. So I think I'm back up and running, and I think I've fixed the problem. So, but I did get the midterms graded yesterday. And if you check your grades, you should be able to download the graded version of your test. And if you have any questions, I encourage you to come to my office hours and we can go over things. I think the class average was a 76. We had, let's see. I don't have a real pretty way of showing this to you right now. I just know that we had, highest grade was a 96.5, lowest grade was a 30. And we had 4 A's, 3 B's, 2 C's, 2 D's, 3 F's. So overall, I think some of those problems on that exam were really long, really long and tedious, and others were a little more straightforward. So I think there was an opportunity to get points on the easier ones, and then some of the harder ones, people struggled with. But again, if you have questions, we can go over that during the office hours. Any questions before we proceed? So in my computer, the issues I was having, I lost all of my handwritten notes from previous classes that we've been in, including our most recent, I believe I lost. But other than that, I have all my other data. So I'm just sharing that with you so I can't go back and grab any of our old notes or bring them up. So we were here, we were working this problem, and so I don't remember exactly where we finished on this problem. So I think what I'm going to do is just kind of start it over, if that's okay with everyone, since you've had the weekend to forget everything. And I also want to point out something that Terrence, I hope you don't mind me calling you out here, but Terrence had included some really cool graphs on his midterm. And, I try and keep up with technology as much as I can, but, I've been using Wolfram Mathematica to do all of my visualizations that I do in class. And that's because, I wrote the programs for these, and I can make them look the way I want them to look. But there's some really good online graphing software now that can do 3D stuff, and Terrence had done that. And what is it, Geogebra is the name of it, if you've seen this before.
Yeah, that's it.
Yeah, if you go here and go to your start calculator, and then there's a graphing thing here, you can go to 3D calculator. And then you can put in, like, I don't know, I haven't used this much, but z equals x plus y squared, something like that. And it's pretty good. I mean, it's pretty user friendly. You can see, 3-dimensional objects. Now, I haven't messed with it too much to figure out like how to do more advanced things in it, but I know, like, if you want to do like a vector function, you do like, what it was, a curve. And then you do like the 3 components. I think you do you do it in a brace? T.
Yeah, you do.
T sine.
Yeah, as long as you have your parameters, you can.
Yeah, something. I think this is right. T goes from 0 to 2 pi. Let me try that. See, yep. No, I didn't like that. Didn't like the brace. I think the braces don't have to be there. No, why didn't it do that? Oh, I have 2 sets of, there we go. There we go. That didn't work.
It can be a little finicky, but like if you just start typing in your parameters, it'll pick up that it's a curve or whatever.
Really, if I just do like t sine t,
and then like enter it in.
yeah, it's not.
You see that arrow button? Like,
Yeah.
you may have to clear that.
Okay. I don't know.
That
Anyway,
should work.
the point is, I got it to graph some stuff, and it was pretty cool. For some reason, it's not taking it now, but you can have it do vector curves, or space curves and stuff. And sure, there's plenty of other applications you can do here, but pretty cool. I like it. So just be aware, there's 3D graphing stuff out there. That's relatively new. Geogebra didn't have. Do you know how recently that came out, Terrence?
I don't. No, I didn't look it up.
I'd say it hasn't been within the last 2 years, because when Geogebra first came out, it couldn't do 3D at all. And Desmos doesn't do 3D either that I know of.
No, it doesn't.
It can only do 2D. So anyways, pretty cool. Technology is getting there. All right, so what were we doing? We were trying to find maximums. We were trying to find the absolute maximum minimum value of a function on some closed bounded region. So we had started off this section talking about how do you find the local max and mins and saddle points of a surface. And we did calculation of capital D to do that. And that's now in the past. What we had started next was how do we find the absolute max or global maximum, highest point and lowest points on a surface if we're restricting the domain to a closed bounded region. So the idea was we have a surface, and if we take that surface, let me get this out of here. Let me just reevaluate this thing. Start the whole thing over here. Yeah, so if we take this surface and we restrict the domain on the ground to a triangle like this, and so here's our domain restriction in 3-dimensional space. If we just plug these points into the surface, then we get just this green part of the surface instead of the whole surface. And what we're trying to do is find the highest and lowest points on that green surface, right? That's what we're doing. And the way I say we're going to do it is, first, we're going to look to find any critical numbers or critical values by figuring out where the partial with respect to f is equal to 0 and the partial with respect to y is equal to 0, which is the same thing we did when we were calculating capital D. We're going to check to see if we have that satisfied. If we do, we're going to look at that point, see if it's within that region or not, the domain region. And then we have to go and move along the boundary. And I said the boundary is the hardest part. You have to move along like this blue line, which corresponds to this blue edge on the surface, and figure out where the highest and lowest points are here. Then you move along this like hypotenuse of the triangle, which corresponds to that black edge of the surface, and try and figure out the highest and lowest points on that. And then move along this red edge, which would be this side of the surface, and figure out the highest and lowest points. And then we'll compare them all and see, what's our biggest and smallest, right? So let's just start this sucker over. Is that all right with me starting it over? Or do you want me to just continue? I can continue from where we were. It's kind of up to you guys.
That's all right.
May as well start it over.
Start it over. Okay. I'm going to go a little faster though. Okay. So I'm going to start out by just graphing the domain over here real quick. The domain in 2-dimensional space, this is the ground, has, let's see, the points 1, 0, which is here. Then we have 5, 0, which is here. And then we have 1, 4, which is here. And so what I did is I said, okay, here's our region, which is this triangle. And then I kind of called these things different things. Like this edge right here, I called it L1, I think. And then let's say this red edge here, I call that L2. I don't know if, is this what I called it last time? I think I did, L3. I think it was L1, L2, L3. So that's our region. And so we're going to start by looking at the inside, okay? And to do the inside and figure out if we possibly have maxes and mins on the inside, we go back to the previous section or previous part of this section. We take the partial with respect to f and set it equal to 0. We're going to find these are the critical points. So, and then we'll find the partial with respect to y equal to 0, and we'll see what we get. So partial with respect to x is just going to be y minus 1. And then the partial with respect to y is, let's see, x minus 2. And if we set those both equal to 0, we get y is 1, and we get x is 2. So again, we've done that already, but 2, 1 is a point. And this is like, it's a question mark. Like this point, first, does it live in our domain, right? So the point 2, 1, I hope it's obvious that 2, 1 does live in here. So we want to keep the point. Had this point been like 2, negative 1, we wouldn't even consider it. We would just throw it out. So we might have, it might be, okay, this could be where we have a max or a min. We don't know yet. We'll have to compare it to other things. So we're just going to keep that, put it to the side and move on. So now what we'd like to do is let's look at L1. So L1, what we had talked about last time is that anytime you're on L1, anytime you're on this line, that you have something in common with all the points. All the points have some x coordinate, and the y coordinate is always 0 because you're on the x-axis, right? But your x is restricted between 1 and 5 because obviously you're moving across from this point across. So your x's have to go from 1 to 5. And so if we restrict our original function f, right? If we restrict this function to just points that look like this, in other words, if we take f and restrict it to points like that, then all of our y's are replaced with zeros, and all we get is 3 minus x. And this is now a new function. I think I called it g. I want to say I called it g. This now we can look at as like a function of one variable, x. And then we go back to Cal 1. Let me do it this way. With x between -1 and 5, we go back to Cal 1 and we use the closed interval method to find the maximum minimum of a function, a continuous function on a closed interval. So that requires taking the derivative, which is just what, -1. And then we take the derivative and set it equal to 0. But if we do that, we get no solutions, right? Which means there aren't any critical numbers within this interval 1, 5. So the only places where we could have a max or min would be at the endpoints. So what I need to do is check the endpoints. And that means I need to figure out what g of 1 is and g of 5. Right, g, the original function. That's the closed interval method. You're plugging the endpoints into the original function. We plug in 1, we get 2. Plug in 5, we get -2. Is this right? Something seems off. Is this what we did before? For those of you who take notes?
Yeah,
Yeah,
that's
is
what we
that-
did.
Okay. So one way you could look at this right now is that we have 2 places of interest from this L1. We have all points that look like this, but we're the only ones that matter to us when x was 1 and 5. So we have point 1, 1, 0. And we know that when we plug that into the original function, we get 2. And then the other one is 5, 0. And we plug that in, we get -2. Does anyone have a question as to where I'm getting this? It's clear? Okay. So we're going to just hang tight on that. We'll just keep that here and we'll come back to it in a minute. Now let's move to, I think last time I did L3 first because I said it was easier. So if we're on L3, those are all the points along this line. And all those points have the same format. They all have 1 as the x coordinate and then the y coordinate is just y. And y varies between, in this case, 0 to 4, because we can go from here all the way up to here. Now, if we take our original function and we restrict it to 1y, then if I replace all my x's with 1s and all my y's stay y's, I should get 3 plus y minus, I'm replacing x with 1 minus 2y. And that should just give me 2 minus y. And again, this is now a function of a single variable. So I can look at it as g again. This time it's a function of y. So g of y is 2 minus y. And my restriction is from 0 to 4. And then I do the same procedure. I take its derivative. I figure out if it's ever equal to 0. And again, the derivative of this is -1, which is never 0. So I have no solutions, no critical numbers, no critical points. So I just check the endpoints. So I want g of 0 and g of 4. And when I plug 0 into the original g function, I should get 2 and -2. So again, we have 2 interesting points here. One, the x was 1, right? Because we were saying 1 has to be x, and then the y could have been 0 or 4. And in the case that it was 1, 0, we got 2. In the case that it was 1, 4, we got -2. So those are 2 interesting points. Do y'all see that on this one, we actually have the same point appear as over here? And that's because that's where the 2 lines come together. That's right there. That's where the black line and green line come together. They should have a point in common, right? And that's this point right here. Questions? Okay, L3 is the harder one. Because on L3, we have points here. They all look a certain way, but it's not as easy because, you know, on L1, the y was 0. On L3, the x was 1, right? But on L2, your x's and y's are changing, right? So what we have to do here, let me take this and copy it real quick. Let me throw that down here. What we have to do in the way that I look at this is I say, all right, well, look, this is a point, right? This is the point 1, 4. And this right here is the point 5, 0. And I know that this is a line, right? I know this is a line. And so if I have 2 points on a line, I can always find the equation of the line, right? I can just use y. I can use y minus y1 equals m times x minus x1, right? That's our point slope formula for a line. Give me any point on the line and give me the slope of the line, I can give you the equation. So I'm going to use this point right here, okay? My x1 is 5, my y1 is 0. Now, can you tell me the slope of this line? Rise over run, right? Rise over run. So the rise here is 4, and the run here is what? Sorry, the rise here is negative. It's a negative rise because we go down. And then the run here is 4. So the slope of that line should be -1, right? So the slope of this line should be -1. Any questions on that? Replace y1 with 0, replace x1 with 5, and we finally get an equation here, -x plus 5. All right, so what is the value of having the equation of the line? Well, the value is that if I pick some random point, right? Let's just take some random point here. I'm just going to call it right here. I hope you can see this x, right? If I pick some value x and plug it in here, the x coordinate will be x and the y coordinate will be y, but that y is this, right? So that means that when I'm on L3, let me come back here. When I'm on L3, my x is x and my y will be -x plus 5. So all points on this L3 must look like this. Do y'all agree? Yeah. And then I can take that and plug it into the original function. So if I take this f of x, oh wait, sorry, what's the restriction on x? I need to put my restriction on x. So what is x bounded between here?
Between 1 and 5.
between 1 and 5 again. Good. So between 1 and 5. And so now I'm going to plug in x, and I'm plugging negative x plus 5 for y, and I'm going to do that into the original function, which is up here, right? I need this. Throw it down here. I'm running out of room. Put it right there. Okay, so now what I'm doing is I'm going to take this equation for f of x. I'm going to replace x with x. Everywhere I see a y, I put negative x plus 5. Okay, so I'm just replacing all the y's with negative x plus 5 and leaving the x's alone. And when I do that, I get negative x squared plus 5x minus x plus 2x minus 10. Check my arithmetic there. Negative x squared, let's see, how many x's? 6 x's, I believe. And then minus 7. Okay. Any questions? All right. Whoa. All right, so here's where we are. And now at this point, we have it down to, again, a function of x. So I'm going to just say, hey, we've got a function of x, call it g again. And it's negative x squared plus 6x minus 7. And it's bounded on the interval 1 to 5. And I need to find the max and mins here. So closed interval method, I take the derivative of this function, which is negative 2x plus 6. I set the derivative equal to 0, which should give you x is 3. I'm not going to show that work, right? That's just a linear equation. Set it equal to 0, and you get 3. So we have one solution here, don't we? We have one solution. So what I need to check are the endpoints and this point, x is 3. So let's start with the endpoints. The endpoints, and this is where things are a little weird. The endpoints, what I'm doing is I'm into G, I'm plugging in, let's see, 1, right? Then I need to plug into G 5. And then I have the critical point, I'm gonna call it CP. My critical point was 3, so I need to plug 3 into the G function. And let's figure out what we get. So if I plug in 1 into G, not G prime, into G, if I plug 1 in here, what do you get? Someone got that for me? Plug 1 into here.
-2.
-2. Okay, what about 5? What happens when we plug 5 in here? So it's gonna be negative 5 squared plus 6 times 5 minus 7.
Isn't that also -2?
It's also -2. Okay. And then I have to plug in 3. So what happens when I plug in 3? Negative, and then I got 3 squared plus 6 times 3 minus 7. Let's see, this is -9 plus 18 minus
That's
7.
11.
11? Is it 11? Hold on.
Just
We get
2.
2, right? Because it's -9.
sorry.
Yeah, remember, you're not squaring the negative. Negative's on the outside here, so you should just get 2. Okay. Any questions there? Okay, this part, just pay attention. Remember how up on the previous one, we said, okay, well, this really means that when we plug in 1, 0 or 5, 0, these are our answers, or 1, 0, 1, 4, these are our answers. We need to do the same thing here. And we have 3 different things. So in terms of a point, we have something becomes something, something becomes something, and on this one, something is going to become something. So remember, I'm plugging in 1 for x, right? 1 is going in for x. What's y? What's the y? I know that -2 comes out, and I know here -2 comes out, and I know -2 comes out. But I'm asking, what's the y coordinate here that I'm plugging in?
Would it be 4?
4, yeah. So you have to go back up to this. while you're on L3, all points must look like x, negative x plus 5. So if you're going to plug in 1 for x, that means the y value you're plugging in is minus 1 plus 5, which is 4. So that should be a 4. Okay. If we plug in 5 for x, then we come up here and we say, okay, plug in 5 here. This should be 0. And if we plug in 3 for x, negative 3 plus 5, that should be 2. And we're done. Well, kind of. We need to go back and look. There was one point.
Sorry, is that
Say again?
on the third point? Is that supposed to be -2 or is that positive 2? It's just a typo on 3-2. Sorry, on 3-2.
Right here? Oh, is this
Yeah,
supposed to be positive 2? Is that what you're saying?
Yeah.
Right here? Yeah, that was supposed to be 2, right? Yeah, thank you for catching that. All right. So I'm gonna do this a little different than I normally do. I'm gonna draw this domain again. Here's 1, here's 5, here's 4. Okay, we had this point, this point, this point. This is the point 1, 4. This was the point 5, 0. This was the point 1, 0. And what I can tell you is that when we plug, let's see, 1, 4 in, we get -2. So when we plug this point in, it spits out -2. When we plug in 5, 0, it spits out -2. What about 1, 0? I'd have to go back up to the previous one, right? At 1, 0, it's going to be 2, right? We got that. And then 5, 0 and 1, 4, we already have. So when we plug this in, we get 2. And then there's this point 3, 2, which is like out 3, up 2. It's somewhere here. And at that point, we get 2 to come out also, right? Which point have we not looked at? The one from the very, very beginning. Remember the one that lived in here? We never checked that one. So we need to figure out what happens when we plug 2, 1 into the original function. So I think we should just do it up here. Let's plug in 2, 1 into here and see what we get. So 2 for x, 1 for y. We get 3 plus 2 minus 2 minus 2. 5, we get 1, right? We get 1. So that means going back down here, I had that point 3, forgot it already. What was it? 3, 1, 3, 2? 2, 1. 2, 1, right? Sorry. It was the point, this one right here was 2, go up 1. This point right here, from the very beginning of the problem, when we plug that point in, 2, 1, it spits out 1. All right, so now we finally answer the question. What is the absolute maximum value of this function? What's the maximum on this closed bounded region?
2.
2. It happens here, here, at those 2 points, right? We get 2. And then the minimum value would be -2, and it happens at 2 different places. Understand? So the final answer is that the absolute max is 2. The absolute min is -2. This point here inside didn't really give us anything. Oh, wait, you know what? Yeah, those 2 points. Okay. So let's take a look at the graph again. So here was the green region, right? We were trying to find the largest and smallest points. And what we just determined is that we should have a max at this point and at that point, right? And then a minimum at these 2. So I'm going to take the domain out of here. I'm going to take the lines out of here so that all we're doing is looking at the surface. And I think you would agree that we have our 2 max points here. Okay, they're both the same height. And then at these 2 corners, we have our 2 mins. And that's it. That only took 30 minutes. All right. Next problem. I'm not going to show you a picture of this one yet. I want us to go through the work first, then we'll look at it. Find the absolute maximum minimum values of this function on this rectangle. Now, you may have never seen this before, this notation. D is equal to the set of all points in two-dimensional space where your x values are between 0 and 3 and your y values are between 0 and 2. So if I go draw this, all my x values go between 0 and 3, and my y values go between 0 and 2. So we have a rectangle. It's the rectangle and everything inside. So we're going to take care of the inside first. Okay, to take care of the inside first, I need the partial with respect to x. I'm finding my critical numbers or critical points. I take the partial with respect to x. Let me get that, and then I'll set it to 0. That's my partial with respect to x. Then I take my partial with respect to y. Let's see what we get here. Negative 2x plus 2. Set these both equal to 0. So if I set this first one equal to 0 here, I get 2x minus 2y equals 0, but that means 2x must equal 2y, which means x must be y. So I don't have a solution here, do I? I just have an equation. But the second equation is nice because negative 2x plus 2 equals 0 means that x must be 1. And if this one says x must be 1, and this one says that x must be y, then this means that y must be 1, right? Because we know that x has to be 1 to satisfy this. So if x is 1, y is 1. So we have this critical point 1, 1, which does live in here, right? 1, 1 lives in here. And because it lives in here, I need to consider it, don't I? Okay, so let's save ourselves having to come back and do this. Let's go ahead and just plug this in. Let's figure out what we get. If we plug in 1, 1 into this function, let's see what it throws out. So 1 here, we get 1 minus 2 plus 2. So you get 1. All right, now what?
Now we have to check our boundaries.
You got to go around the boundary. How are you going to go around the boundary? You could do like this right here. Call that L1. Here, L2. Here, L3. And here, L4. The good news is that they're all lines, right? And so lines should be easy for us to figure out what's going on. Go ahead and grab this because I'm going to need it here. Okay, let's talk about on L1 first. Okay, on L1, Reagan, are you here? No. You know what? How about I just call him here? How about Abi? Oh, okay.
Yes, sir.
Yeah, your video just went away. Sorry. Okay, Abi, can you tell me what all the points on L1 have to look like in terms of an ordered pair? Everything on L1. You're muted.
X values have to, sorry, X is X and then the Y value is 0
Yep. And how about the bounds on the X?
between 0 and
0 and 3. Okay. And now we take that and we plug it into the original function. All things that look like this. And all we get there is x squared, don't we? Okay, and now this is a function of a single variable x. So I'm going to call that g of x. I'm going to take its derivative. I'm going to take derivative and set it equal to 0. And I just get 2x equals 0, which gives me x is 0. I have one solution. So now I need to check this answer and the two endpoints. But do you see that this 0 is actually one of the endpoints just coincidentally? Okay, so it just happened to be that way. So I need to check now g of 0 and g of 5. So when I plug 0 into the original function, I get 0. And when I plug in 5, I get 25.
Why 5?
Pardon me? Say again?
G of 3.
Oh, I don't know why I did 5. Yeah, thank you. I'm glad you pointed that out. Why did I do 5? Has 5 been anywhere in this problem? Wow.
It was in
No
the last
idea
problem.
where I pulled that 5 from. Okay, sorry about that. 9. Thanks for paying attention, Gregor. So 3, I need the endpoint. Boom, it comes out 9. Yes? Okay, so in terms of points, when I look back at this, right, and I say, okay, all my points here had to look like x0. I had 0, 0. And then now I had 3 for x, so 3, 0. When I plug in 0, 0, I get 0. When I plug in 3, 0, I get 9. So in terms of comparing things, I already know that this 1 that we found up here, right, at 1, 1, that point, I already know that's not going to be a max or min, right, because it spit out 1. I already have a smaller number and a bigger number. But I have to do 3 more lines, right? I've got to move along L2 now. So for L2, all right, Adam, what do you got for L2? What do all the points on L2 look like?
L2 would be, so you would make the F would be 0 and Y, or no, 3 and Y.
3 and Y. Okay, and what's the restriction on Y?
Y is going to be between 0 and 2.
0 and 2. Everyone follow that? And then we just go through the same process. Okay, I take my original function, I plug in 3y into it. Now here's the original function. I'm going to replace all my x's with 3s, so 9 minus 2 times 3. I'll leave my y alone, y plus 2y. That look right? 9 minus 6y plus 2y, so minus 4y. All right, do you want a shortcut? You like shortcuts? This function right here is a line, isn't it? It's linear. This over here was quadratic, but this is linear. Anytime you have a linear function, your max and mins have to be at the endpoints. In other words, you don't need to go and take the derivative if it's a line, which it is, okay? Because if you take the derivative of any linear function, what do you get? Some constant, right? And that constant being equal to 0, there won't be a solution. So you'll never have a critical number on the inside of the interval. It'll always be at the endpoints. So I'm going to save myself some time. Okay. I'm going to call this thing g of y equals 9 minus 4y. But then I'm just going to skip right to the endpoints because it's linear. So I went g of 0 and g of 2. If I plug 0 into g, I get 9. And if I plug 2 in here, I get 1. So this tells me all the points on L2 had to look like 3s as the x. And then now I had 0 here and 2 here. This spit out 9 and this spit out 1. Every time you do this, if these are like L1, L2, L3, L4, you'll always have overlapping points where the two lines come together. That's just the nature of the beast. All right, we got to go 2 more lines, right? 2 more lines. So now I want L3. So for L3, let's see, Daniel, you're up for L3. What do all points on L3 look like?
All points on L3 are going to look like, what is that, 2x? And it's gonna,
Two-
yeah, 2x?
Well, the X will always be what? The X will always be some value here, right? Between 0 and 3.
Yeah,
And the Y value will always be 2.
yeah.
Okay, so it should look like X2, like
I'm
that,
still
right?
I'm still waking up. I just had them flipped.
It's all right. And then the bound on X, let's see, X would vary between 0 and 3, right?
Yes.
Okay. And now we need to plug this into the original surface function. So all the X's stay X's. All the Y's become 2's. So we get X squared minus 4X plus 4. We all on board with that?
Mm-hmm.
Okay, now this is not a line, right? So I can't just go straight to the endpoints like we did here. So I'm just gonna have to say, all right, well, this is some function of X on this interval. Take derivative. Set to 0. X is 2 is our solution. And now I need to check. I need the endpoints. And I need that critical point too. So I'm checking these two endpoints and I'm checking this and I'm plugging those into G and seeing what I get. I plug 0 into G, not G prime, but into G, I get 4. If I plug 3 in here, okay, I'm gonna have to do this in my head. 3 squared is 9, 9 take away 12, -3, and then add 4, so 1. And if I plug in 2 into this, let's see, I get 4 minus 8 plus 4. I think I get 0 there. So we know something spits out 4, something spits out 1, something spits out 0. Okay, so remember the X coordinate is the X and the Y is fixed at 2. So all these are 2's. And it's 0, 3, and 2. All right, one more line to go. That's fun. Any questions? Is there an easier way? All right. Okay, on L4. On L4, all the X's are fixed at 0 and the Y's vary between 0 and 2. So all the X's are 0s, the Y's are just free to vary between 0 and 2. I plug that into the original function. So if I replace all my X's with 0s, that's good because all I get is 2Y. Donald, what do you think? You there? Donald? Donald? No? Margie, what do you think?
I think that it's another one of those linear ones, right?
Yeah. So we don't need to even worry about taking derivative, right? So we'll
Correct.
just call this G of Y equals 2Y. And now let's just check the endpoints. So we're going to plug in 0 for Y and plug in 2. Good. That's what I was hoping you would say. It's linear. Let's just get right past the derivative part and just get to this. We plug in 0, we get 0. We plug in 2, we get 4. Now that corresponds to some real points on our graph. Let's see here. All of them had to look like 0Y, so they both have 0 for the X. And the Y's are going to be 0 and 2. All right, there we go. What is the maximum value? Let me zoom out a little bit so we can see this whole thing, all the work we've done. I think this includes everything, right? This has this point we got with in the beginning. It's got these two, these three, and these two. So what is our absolute max?
It's 9.
9. Now, at how many different points does it occur?
It occurs at least 2 points, 3, 0, and 3, 2.
3, 2, 3, 2, we didn't get 9.
Oh, I'm sorry, I misread that one. It's, I'm
Yeah,
sorry,
yeah.
so just 1 point.
Yeah, just 1 point. So we get an absolute max. It only happens at one place. How about the absolute minimum? What's the absolute minimum value?
It's 0.
0, right? 0 is the smallest number we get out, but it occurs at how many places? 0, 0, right? And 2, 2, right?
And 2, 2.
It's happening at 2 different places. All right, now, are y'all ready to look at the picture? Y'all ready to see what this looks like, what we just did? We said, all right, take this surface, here it is. Restrict it to this rectangle. Here's the rectangle. Here's the rectangle in 3-dimensional space. We just determined that if you look at just that surface above, I'm gonna try and make this a little bigger if I can. So if we look at the green, that's the surface restricted to that domain. I'm gonna take domain out of here. There it is. Then we determine that there is a maximum point right here. And we got that when we plugged in, what was it? 3, 0, right? And then we had 2 minimums. Can you see the minimums down there? Here and here. And at both those points is where we get 0 to come out. Okay. What do y'all think?
Not super hard, but fairly tedious.
Yeah. How about this one? I guess the thing that can start getting more complicated is the bounded region. Because if we have lines, we can come up with some restriction on the coordinates, right? We can be like, oh, okay, you know, the X must be 0 and the Y can vary, or the Y must be 2 and then the X has to vary. And then we can do it. But what about this one? Look at the domain, the region. D is equal to the set of all points where X is greater than 0 or equal to 0, Y is greater than or equal to 0, and X squared plus Y squared is less than or equal to 3. Can somebody tell me what that looks like? Like, what does that region look like? I'm going to draw it over here. Do y'all know what this looks like? X squared plus Y squared less than or equal to 3.
This whole thing's going to be the inside of a half circle.
This is a circle, isn't it? Of radius square root of 3, right? Like if this were a 9, the radius would be 3, but in this case it's 3. So the radius of this thing is square root of 3, and it's less than or equal to it, so which means it's the edge and then everything inside. But X and Y both have to be greater than 0, which means you have to be in the first quadrant. Right? X greater than 0 is to the right of the Y-axis, Y greater than 0 is above the X-axis. So we have something that looks like this. This is root 3. This is root 3. And then we have that. So it's like a disk of radius square root of 3, but only in the first quadrant. That's our region. We want to see what the maximum value of this surface is and the minimum value on restricted to this. So are these obvious to you that we can do this boundary, call that, whoa. We can do this boundary Call that L1 and maybe do this boundary and call that L2. Those should be pretty easy to do, right? I mean, easy in the sense that it will be just like we've done before. But what about this edge? How we can do that? I'm not going to call it L1 because it's not a line, or I'm not call it L something because it's not a line. I'm going to call it C1 for curve 1. So let's do the easy ones first. We have to first do the partial stuff, right? That has to be taken care of first. So if I take my partial of f with respect to x, let's see, that just gives me y squared. If I take the partial of f with respect to y, that just gives me, what, 2xy? Set these both equal to 0. This one's the easy one, y is 0. Once I know that y is 0, uh-oh. If what? If y is 0, then what is x? Think about it. If y is 0, then what is x?
Your x could really be any value.
X can be anything, right? Think about it. If I replace this y with 0, this whole thing will be true, and regardless of what I let x be. If I let x be 2, this would still be true if y is 0. So what we have is something uniquely different. We haven't had this before. So y being 0 means that x here is free, right? Free meaning it's a free variable. It can be anything we want it to be, which means that the points that make these true must look like this. X is free and y is 0. X is whatever x is and y is 0. However, do y'all see where that is here? What is that over here?
L1.
It's really L1, right? We got lucky, okay? Because L1 happens to be include all of these points. All right, so because of that, because this is actually L1, I'm just going to skip this step and just go to L1 now. All points on L1 look like x0, where x is bounded between 0 and the square root of 3. Now I take my original function, I restrict it to x0, and well, that's easy, isn't it? If I restrict this to x0, what do I get? 0, right? Okay, so there's nothing to check here. What I can tell you is that if you take any point along L1, any point, the output's 0, right? So for any x0 that you plug in, the output of the function is going to be 0. Move to L2. What do all the points on L2 look like? This time, x is 0, right? And the y is, well, anything between 0 and square root of 3. But again, when I take those points and plug them into the original function, well, if you're letting x be 0, it's going to kill everything off, and you're just going to get 0 again. So that tells me any points along that edge are going to spit out 0. So there's only one thing left, right? There's only one thing left, and that's C1. So how are we going to do C1? I'm going to try and squeeze it in right here. How are we going to do C1? Can somebody tell me what all the points on C1 look like?
X squared plus y squared equals 3.
Okay, yeah, they do have to satisfy that equation. X squared plus y squared has to be 3. That, to be a point here, you must satisfy that equation because you're on the edge of the circle, right? But I need a relationship between x and y. So what I'm saying is if we let x just be x, right? So just come in here, plug in some x value. Can you tell me what the y value has to be? Why don't you take that equation, solve it for y? Solve that for y. Now, technically, I'm supposed to take plus or minus, right? Because I took the square root on both sides. But because we're looking at the top half of the circle, we're only going to take the positive square root here. So it's very important that you understand, I'm only looking at the positive because we're on the top. So that means all my y values have to look like this. Oops. And our x's here are stuck between 0 and square root of 3. Does anybody need any clarification on this, the way all the ordered pairs look for C1? Rabi, you're good?
I'm lagging pretty badly. It didn't catch.
Oh, your video's lagging. Okay, got you. I'm not sure if I repeat myself if it's going to help if your video is lagging. What are we going to get if we plug this into the original
Cutting
function?
out.
What are we going to get when we do this into the original function? So we replace, oops, sorry, we replace x with, well, x, we leave it. And then the y, this y we replace here and we square it. Oh, thank goodness we square it, right? Because then we just get 3 minus x squared. Right, we take the square root and square it. And then that just becomes 3x minus x squared. Now that's a quadratic, right? So we have to go through the process here.
Isn't that x cubed?
Pardon me?
Isn't that 3x minus x cubed?
Oh, x cubed, yeah. And Gregory, you get the award for sharpness today. Distribute 3x minus x cubed. So it's non-linear, so we have to, let's define this as a function of a single variable on the interval 0 to square root of 3, and then differentiate. And then set that derivative equal to 0. And we should get there x equals plus or minus 1. You should get 2 solutions there.
No.
Say again?
Thanks.
Adam, did you say something?
Nope.
No? Okay. Now, one of those solutions I can throw away. Which one am I throwing away? Can x be
Negative 1.
Yeah, look where we are, right? X and negative 1 is over here, so we can throw that away. So now I'm going to check the endpoints. So I want g of 0, g of root 3. And then I want that critical point, which is g of 1. Yeah. Okay, when we plug 0 into the g function, right? We're doing to the g. We get 0. When we plug in root 3, we get 3 root 3 minus root 3 cubed. And then when we plug in 1, we just get 2. You'll give me a second. Hey, did I leave it longer? No, actually, okay, all right, I'm in the middle of class. Okay. Any questions? No? So from this, we have some points that are spitting out some answers. All right, so let's start with this first one. We plug in 0 for x. The y coordinate will be, all y coordinates have to look like this right here. So 3 minus 0, that would just be √3. And when we do that, we get 0. And then when we plug in √3 for x, what do we get here for the y coordinate? If we plug in √3 right there for x. So √3 squared would be
3
3.
minus 3.
3 minus 3, which is 0. Square root is 0, 0. So we get a 0 here. And that spits out 3√3 minus √3 cubed. And then if we plug in 1 for x, now if we put 1 in here for x, we get 3 minus 1, that's 2. We get square root of 2 here, and it spits out 2. Can you tell just by looking right now what the global max and min is, or do we need to do a little more?
Doesn't 3√3 minus √3 cubed become 0?
Yeah, so you have to just do some algebra on that and convince yourself that that's 0. Right? You could just say, this is √3, √3, √3. That's what that means. And then those two together give you 3, and that's 3√3. So that gives you 0. So what's the absolute max? And what's the absolute min? We only have one
Absolute
max, right? 2. Max is
Yeah.
2. Only happens at one place. The minimum value is 0. Now, the minimum value actually occurs at infinitely many places. Let's take a look at this example. Here's the surface, pretty cool looking surface. If we were to take that surface and restrict it to just our domain, we just get that little piece right there. You just get that little piece of it. And what we just determined was that the max occurred right here at this top point, right? That was the only place it occurred. And then actually our minimum values are all along this edge and all along that back edge too. So we had an infinite number of places where we achieved our minimum value. Now, I know right now you're sitting here going like, why would we use this? Where would we need this, right? Look, it's just right. If you go back to Cal 1, when you're learning about max and mins of functions, it was all leading you into optimization problems where you have like, you know, a farmer wants to build a fence, blah, 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 you know, and then you get the function for the area or perimeter or whatever it is or cost, and then you maximize or minimize it. This is the same exact principle here. We're just getting the mechanics down so that now we can start putting these into word problems where we're trying to find the max and min of something. But the great news is now we can work with functions of 2 variables. Okay, and that opens up the world, a world of possibilities in terms of what we can and can't do. All right. So here's an example. Okay, this is the last problem in the section. Find the volume of the largest rectangular box with edges parallel to the axes that can be inscribed in this ellipsoid. So you have an ellipsoid. I've given the equation right here. There it is. And you're trying to figure out what the volume of the largest possible box, rectangular box you can put in here is. So you can, let me see, there's my, let me pull that out here. So one thing I could do is, you know, I could change it and make it a very tall box, right? Very tall, and I'll get a certain volume. I could widen out the box. Look at my volume just went up, didn't it? It's bigger, 9, oop, right around there, 9 something. But if I go too far, it becomes shorter and wider, but now the volume's less. There's an optimum set of dimensions for this box that gives me the most volume possible. You ready to try this? You understand the context of the problem and what we're trying to do? So with any problem that we ever did in Cal 1 where you're trying to find like the maximum or minimum of something, you've got to come up with a function that represents the thing you're trying to maximize or minimize. In this case, we're trying to find the maximum volume of a rectangular box, all right? So if I have a box, right, we know that the volume of this is length times width times height, right? That's everyone knows that, right? But this box must be inscribed into the ellipsoid, which means that the edge of the box, right? The edges of the box must touch the ellipsoid, right? Those edges must be touching the ellipsoid. That's important. That's important because if the ellipsoid is centered at the origin, then that means that this box is centered at the origin, right? The box should be centered at the origin also. So can somebody tell me, you have to imagine that, you know, I don't want to, let me go back to the picture. It might be helpful if we have the picture here. Okay, so here's our ellipsoid. Yeah, that'll work. Let me do something. It's kind of distracting me. Where is it? Where is it? Okay, hold on. I've got to figure out where this is. Shit. There we go. All right, so back to this. I'm going to pull this ellipsoid out a little bit. All right, so the center, let's start at the center of this thing and talk about this point. I have to go out a certain X value, then a Y value, and then a Z value. All right, that's terrible. To get to this point, I have a certain Z value. Right? So I have to go out X, Y, and then up Z. So the coordinates of that point right there are X, Y, Z. Agree? But because that point lives on the ellipsoid, do you also agree that this X, Y, and Z have to satisfy the original equation of the ellipsoid? Right? So this, whatever this is, has to satisfy the original. So watch, I'm going to have to grab this here, because that's a pretty good picture. So if this is the point X, Y, Z, can somebody tell me what the volume is of that box? Be careful. What is the volume of that box? If this point is the point X, Y, Z. Be careful.
Um, 2x, 2y, and 2z,
Yeah, why are you saying 2?
because it's going away from the axis on both sides.
Yeah, so this point right here, this distance from here to here is X, right? But the box goes in the other direction also. So the distance this way is actually 2x. This from here to here is Y, but it goes the other direction also, the same distance. And if this is Z, then it goes the other direction down that much. So this should be, good, Adam, 2x times 2y times 2z, which is really 8xyz. We want that's our volume, right? And we want the maximum of that volume. Do we know how to find the maximum of functions? Do we? Max and mins, okay. Do we know how to find the max and min of a function of one variable? Yes, Cal 1. Do we know how to find the max and min of a function of two variables? Yes, that's what we're doing here. But this volume function has how many variables? 3. We don't have a method for that, do we? But maybe there's a way we can get it down to 2. Maybe we can get this down to 2 variables. And this is where you have to bring in the fact that it lives on the ellipsoid. If this point lives on the ellipsoid, then can't you solve this for Z? Could you solve this for Z? And if you solve it for z, wouldn't everything you have there have x and y in it? Right? You would have x and y. And so what you would wind up with is a function of x and y. I'm going to do it now. I'm going to just solve this for z. So first thing I'm going to do it right here. I'm going to just leave the 4z squared here and then go 36 minus 9x squared minus 36y squared. So I just move the x and y terms to the other side. I'm going to divide everything by 4. And then I'm going to take the square root. And I'm going to do the plus. And the reason I'm only do the plus is because the z in our picture, we went up, right? We went up, so I'm assuming that the z is positive. Any questions? Okay, here we go. I would like to write the volume formula again, but I'm going to need some space. So the volume now is actually 8x times y times z, but z is the square root of 9 minus 9/4 x squared minus 9y squared. Okay. Now, the volume is now a function of two variables, right? You only see x's and y's. Okay, here we go. Now, this is a real important part. Right now, when we have a function of two variables, we have two different ways to go about it. We can either try and find local maxes and mins, or we can try and find absolute maxes and mins on a closed bounded region. For this particular problem, do we have a domain restriction on x and y? Do we?
Yes.
What's that?
Yes, we do have a domain restriction.
Absolutely. If we look at this ellipsoid and where it cuts through the XY plane, what we would have is, it's hard to draw it on here, but we would have like, oh, that's terrible. We would have an ellipse, wouldn't we? Where this egg cuts through the XY plane, we'd have an ellipse. And that means all of our x's would have to come from it. Our x's and y's would have to come from that ellipse. So it looks like at this point, we're going to have to do the closed interval method or closed bounded region method, which is going to suck because doing an ellipsoid in two-dimensional space, or an ellipse, sorry, then we can do the inside part using the partials equal to 0, but then moving along the boundary, right? Moving along that boundary is going to kind of suck. You understand what I'm saying? But what if, just think about this logically, do we even need to consider the boundary? Think about any point that would be along this boundary. Think about any point that would be along that boundary. Why am I not drawing? It's not one to draw on top of. Okay, I'm going to clear this out. Here's what I'm doing. I'm going to draw that ellipse like this again. Bad. What if your point was on this boundary? What can you tell me? Come on.
Oh, that the rectangle is outside of inside the ellipsoid. It's no longer inside only.
And the volume of it would be 0.
Okay, why would the volume of it have to be 0?
Because it'll be on the XY plane. So
And if you're on the XY plane, what's Z?
Z will always be 0.
And if Z is 0, then your volume is 0. Agreed?
Oh, okay.
So does that make sense to everyone? Even though this looks like a closed bounded problem, we can tell what's happening on the boundary already. Because if you're on the boundary, you're on the XY plane. If you're on the XY plane, then Z is 0, Z is 0, the volume 0. So if there's gonna be a max, it's gonna have to be on the interior of that. And the way that we do that is just by setting the first and second partial, or first partial with respect to X and partial with respect to Y equal to 0. If we can solve that, we're done. But it's the partials that are about to suck, okay? Here we go. You ready to take some partials? Oof. Oof. Okay, so the max or the min must be inside ellipse domain. Okay, that means just need where the partial of f with respect to x is 0 and partial of f with respect to y equals 0. All right, that's all we need to figure out, and that's where we should have our max and min, or our local, that's where we should have our local max and mins. All right, so let's start with partial with respect to x. All right, this is terrible. So we have to take derivative of this with respect to x. I have product rule here. So derivative of this first part with respect to x is 8y times the square root. Can I say square root of junk? Because that's what it is. Okay, I'll come back and figure that all out later. Okay, plus now I need the derivative of the square root of something. So we all know from taking Cal 1 and Cal 2 that anytime you take the square root of something, you get 1 over 2 times the square root of that something. Times, chain rule, derivative of what's inside with respect to x, which would just be -9/2 x. And then finish off the product rule by multiplying by the front, 8xy. All right, everyone see that's the product rule there? All right, I'll come back to that. Let's find the derivative with respect to y. It's almost the same. It's product rule again. So we have to take derivative of that front part, which is 8x times the square root of the junk plus the derivative of the square root of the junk, which is 1 over 2 root junk times, now the derivative of the inside of this with respect to y is a little different. It's just negative 18y. That's just derivative of that piece. And then times the front part, which is 8xy. There we go. We get to set these equal to 0. So I'm going to clean this one up over here. 8y. I'm going to call this root j. Okay, I really want to get lazy now. Plus, no, it'll be minus. Minus, let's see what we can do here. 2 and 2 there. Those 2's together become a 4. And that 4 goes in the 8 twice. And then I can put it with a -9. So we should have 18 xy over root junk. Following my algebra here? Just cleaning up the numbers. 2 times 2 is 4, goes in there twice, hits that, -18 x, oh, x squared y. Oops, I almost missed that. X squared y, right? X times y over the root junk. Let's do the same thing on this one. This will be 8x root junk. Let's see, minus, what do we get as our number here on this one? Is that minus 72? Yeah, minus 72 xy squared over root junk. Now, if I wanted to set this equal to 0, right? If I want to set this equal to 0, then what I would do is I would want to try to get a common denominator. I need to go to a new page. How are we doing on time? Okay, so I need to get a common denominator. So I'm going to go ahead and do that now. If I got a common denominator here, this is over 1. I would have to do root junk here, right? That's what would happen. And so I get 8y. And then when the root junk and root junk come together, I just get the junk, right? On the top. And then minus 8x squared, 18x squared y all over the common denominator root junk. Same thing over here. If I put these two together, I do, this over 1 and do root junk on top and bottom. I get 8x times junk minus 72xy squared over root junk. All right, I'm ready to ask the question. When is the partial with respect to x equal to 0? Well, a fraction can only be 0 when? Fraction can only be 0 when?
0.
When the numerator is 0. So I need to know when 8y times junk minus 18x squared y equals 0. Similarly, on the other one, if I want to know when f partial of f with respect to y is 0, I want to know when 8x times junk minus 72xy squared equals 0. Is this starting to look pretty bad? These two equations, we can try and set them equal to 0, right? We can try and set them equal to 0. But we have like 2 variables in each one. So it's going to be impossible for us to get an easy answer unless we can factor it. Why don't we try this? Why don't we set them equal to one another? Because they both have to be equal to 0, right? So let's set them equal to one another and see if it gets us anywhere. If I set 8yj minus 18x squared y equal to 8xj minus 72xy squared, then maybe I can solve this. Maybe, no promises. Is there a number that goes into all those?
Zero?
Well, I'm saying, is there a number, the coefficients? I'm just trying to clean it up. Like divide everything by, can we divide everything by 2? Just to make our numbers a little nicer. Two goes in there, what, 36 times? What a disaster this is, right? Isn't this becoming an algebraic disaster? So I'm going to try and move everything to one side. Do y'all buy that? Everything came to one side. I have 4 terms. I'm going to try grouping. No promises here. What can I pull out of the first 2 terms? 4j, right?
Right, 4j.
And I'm left with y minus x, right? What can I pull out of the other 2? Can I pull something out?
9xy.
2.9.
9xy, and what am I left with?
4y minus x.
4y minus x equals 0. Did that work? I mean, I did factor, but is this okay for grouping? Don't you have to have both of these match? Right? Don't those have to match for grouping to work?
Yeah.
And they don't match. So what we've run into here, and I think this is a good point to stop the problem, because what we've run into is a problem that seems reasonable to ask, okay? We know what we need to do, right? We need to maximize the volume equation or volume function. It was a function of 3 variables, but we were able to use the fact that the point lived on the edge to get it down to a function of 2 variables. However, like mechanically, we know what we need to do. It's just the algebra becomes somewhat of a nightmare now, right? Do y'all agree that that's a nightmarish problem now? I mean, I went and said, okay, let's set them equal to one another, and it seems like we're stuck. Maybe we should have stuck with this and set it equal to 0 and tried from there, right? I mean, like, there's still more algebra we can do, right? So we're seeing immediately with this problem, there's limitations to what we can handle doing by hand. But that's what the next section is about. The next section is going to make this problem look easy. All right. So I think this is a good point for us to say, I give up. Okay. All right. For now, we give up. All right. We're saying this is just looking like a nightmare. All right. I surrender. The math wins. So it was, we're going to answer that question. Don't worry. We'll come back and do it. All right. I just want to leave it as an open question. So we're at a point where the theory is in place. Okay. The theory is in place for us to be able to find max and mins of functions. Right. It's there, but we don't have something easy where the algebra can still be a problem. Right. So we have this new method. All right, it's called Lagrange Multipliers. And I think I told you this section usually causes students a lot of grief, all right? Because there's a lot of mechanical stuff you have to do, algebra here. But the actual method is beautiful because it makes very hard problems easy. All right, so Lagrange multipliers, the way it works is this. I'm going to show you what it is first, and then I'm going to try and visually explain what's happening. Although the visual explanation is hard to convince you of. We've already learned from the previous section that we can find local max and mins and saddles by doing capital D calculation. We also know how to find the absolute max and mins of a function in a closed bounded region. L1, L2, whatever, move around, do your thing, right? As long as the algebra doesn't get too bad, we can do those. We now develop a very powerful method for finding the maximum and minimum values of the subject of a function subject to some constraint. Okay, so that means we're going to start with some function and we're going to constrain it. That's like a domain restriction. We're going to make some sort of domain restriction, which is kind of what we were doing just now, but a new method. And here's the way it works. So this is the method of Lagrange multipliers. This is what you do when you have a function of 2 variables. So let's say you're given a function, right? This is what we've had, some function of 2 variables. And let's say that I have a constraint. Now, this constraint may not make sense to you right now, but let's we'll just put it down and we'll see what it means in a second. So we've got a function we're looking at, and we have a constraint equation. Do the following to find the maximum and minimum values of that function f. So first, we will find all values x, y, and lambda. This is a new variable. It's the first time you've seen it here in this class. We're going to find all the values of x, y, and lambda such that, y'all remember this symbol? What does that stand for? The gradient. All x, y, and z such that the gradient of f is equal to lambda, which is some constant, times the gradient of g. And g of x, y must equal k. Once you find all the points that satisfy those 2 equations, then you will evaluate f at those points, and the biggest answer you get is your max, and the smallest you get is your min. All right. I understand that the first time you see that, you're like, what? What are you talking about, right? This makes no sense. So I'm going to show you, you know what problem I want to do? Yeah, let's just look at this one visually. So right here, what we're looking at is this function f of xy equals x squared plus 2y squared. There it is. And I'd like for us to look at this function constrained to this equation, x squared plus y squared is 1. Meaning that's a circle, right? Circle radius 1. You're only allowed to plug in points off this circle into the function. And so if I plug just these points into that function, we would get a curve that lives up on that function, wouldn't it? Be a curve like that? And we're trying to find the highest and lowest points. So that's what it means when we say take a surface, constrain it to an equation. So constrain the domain, only allow those points to go into the function, and then find the highest and lowest points on that curve that basically you created. Lagrange multipliers will allow us to find those. All right, but we have to do some calculations. We have to make sure that these two equations are satisfied. Right? So let's do this example. I don't know if I'm gonna have enough time. We'll spend all of next class doing this, so don't get too freaked out. All right, this right here is our constraint. We call that g of xy, and then equals k right there. And then this, of course, you know, that's your f of xy right there. According to the Lagrange multipliers method, oops, wrong one. What we need is this to do this. Make this small here. So we want to find all the values x, y, and lambda such that those two things hold true. All right, so let's just talk about what those things are. What is the gradient of f? Anyone remember what the gradient of f is? It's a vector. It's a vector. It's two components because f is a function of two variables. It's just the partial of f with respect to x, partial of f with respect to y. That's the definition of the gradient of f. So for us in this particular problem, that is just 2x, 4y. Do you all agree that that's the gradient? Okay, we need to make sure that that gradient is equal to lambda times the gradient of g. Well, let's find the gradient of g right now. So that's g, partial g with respect to x, partial g with respect to y. So what is a partial of g with respect to x?
It's 2x,
2x. Partial of g with respect to y?
2y.
2y. Okay. So now let's see, we need part one up there to hold, right? We need part one. We need the gradient of f. I'm going to write it a little different, to be equal to the lambda times the gradient of g. The gradient of f is 2x 4y. That must be equal to lambda times the gradient of g, which is 2x 2y. According to Lagrange's method, if I can figure out if we can figure out the x, the y, and the lambda that make this true, okay, we need this to be true, and we need this to be true. The constant equation must be maintained. Then we will have found where the max and mins occur. So here's where I'm going to go from this now. If these two vectors have to be equal, then I can distribute lambda through here, make that 2 lambda x, 2 lambda y, must equal 2x 4y. So the only way two vectors are equal is if their components are the same. So I'm going to set up my first equation that must be true. The first equation must be true is that this must match this. Those have to be identical. 2x must be 2 lambda y, or 2 lambda x. The second equation I have is that these have to be true. Those have to be equal. 4y must equal 2 lambda y. And the third and final thing that must be true is that last condition up here, which was g of xy must be k. And this is g of xy must be k, so that's the actual constraint equation. And it will always be the constraint equation. Questions? Is that 4 minutes? Let's find the x, the y, and the lambda that make all three of these equations true at the same time. Now you may be thinking, oh, I'm trying to solve a system of equations. 3 equations, 3 unknowns. The problem is that this is not, you can't use matrices because these are not all linear equations. Look at your last equation 3. It's non-linear. And so you can't use matrices. All right, so we just have to do algebra. So let's start with the first equation. One thing I can do algebraically on this first equation is I can divide both sides by 2. That I'm allowed to do, right? Now, I'm going to work with these equations separately. So, all right, so that's that one. Now, you might be tempted to divide both sides by x. Do not do that, okay? That's a bad algebra move. Instead, bring everything to one side. Move your lambda x to the left, then factor. And when you do that, you get 2 solutions. Do you all agree with this? In order for the first equation to become true, I must have that x is equal to 0, or, that's an or, not an and, or lambda has to be 1. That's what would make the first equation 0. I mean, sorry, the first equation true. Let's do something similar to the second equation. If I move everything over to one side, I could have divided by 2, but I guess I'm not going to. So move that to the left, factor out a 2y. I get 2 answers. Y must be 0 or lambda must be 2. Any questions? I've got 1 minute. Here's where the part of Lagrange gets confusing to people, I think, is what you need to figure out is the x, the y, and the lambda that make all 3 of these true at the same time. So let's take this case right here. What if x is 0? Okay, so I'm going to put that down. Let x be 0. Now, if x is 0, the first equation is true, right? Equation 1 is good. Now, equation 2 is not good yet. If x is 0, x has no impact on this. So what would I need to do to make the second equation true?
Set lambda equal to 2.
I can go lambda equals 2, right? Or I could do y equals 0, right? Either one. Let me do those one at a time. Let x be 0 and let y be 0. Let's just look at that case right there. If x is 0 and y is 0, do you agree that equation 1 and equation 2 are satisfied? But what's wrong with this?
Equation 3 isn't.
Yeah, if you go to equation 3 now, and if you said x is 0 and y is 0, then you get what? 0 is 1. And that's not right, right? So you can't let x be 0 and y be 0. So we're done there, okay? The other thing we could do, let x be 0 and let lambda be 2. That would satisfy both these equations, wouldn't it? X being 0 and lambda being 2 will take care of equation 1 and 2. And now go to equation 3. If we go to equation 3, what does equation 3 become if we're letting x be 0? Y squared is 1, right? If X is 0 in equation 3, and that means Y must be plus or minus 1. So here's what we have. In this particular case, we have that X could be 0 and Y could be 1, or we could have X is 0 and Y is -1. And of course, with both of these, lambda would have to be 2 on both of those. And that right there, these are our candidates right now for where we're going to have a max or a min. Do you see I've found an X, a Y, and a lambda that make all three equations hold at one time? Yes? But I'm not done. Why am I not done? That was just X being 0, right? Now I have to say, well, what if lambda's 1? And look at that. And then I have to look at, what happens when lambda's 1? Okay. What happens when Y is 0? What happens when lambda's 2? I have to go and exhaust all these possibilities. And some of them will be dead ends and you'll be like, nope, can't be that, can't be that. But you have to look at every single possible combination. And so, it's going to get tedious. We're out of time. We're going to have to pick up this problem when we come back. All right. I'm going to have to leave pretty quick. If you have a question, I can answer it quickly, but I will have to take off. So